to look at project 5. The first problem here, the first page, and there's a different problem on each page. And for the first one, I just want you to scroll through this table and put numbers in here. And then as you look at the whole table, answer these two questions. There's one question related to this table, and there's another question related to this table here. And so I want you to consider how long it's going to take for you to accumulate $1 million in your lifetime. It's not hard if you have 40 years in your work life and you're saving a little bit every month. It's not hard to become a millionaire. And so that's what this one's all about. How long will it take Dot Snice to accumulate $1 million? So in the future, she wants to have $1 million. She invests $3,000 per year. So the way that that's written, it's $3,000 per year. So once at the end of the first year, another time at the end of the second year, another time at the end of the third year. She's making regular payments. So that's going to be our payment amount. We're going to start with $0. And after the first year, we'll have 3,000. After the second year, we'll have 6,000 plus a little bit more in interest, and so on. The rate is 8, interest rate of 8, and interest is compounded annually. So that's one time. All right, so we've got everything we need. We're going to use the TVM solver. Now, what's different about these problems is these are all future value problems. So if you want to see some examples related to future value, then you need to go to the section that we covered the last time. Now, it's N that we want to calculate here, because it says how many years will it take you to accumulate $1 million? Can you do it in your lifetime? Let's see. The interest rate is 8. The present value is 0. The payment is $3,000. Will you ever get to $1 million? So this is the setup. Now, because the payments per year, compounding per year is 1, remember N is 1 times M. And if the M is 1, the N is going to be equal to the T. So this gives you the number of years right here. And we'll solve that. And it's going to take 43 years. Do you understand what that means? You understand how powerful that is? If you want to have $1 million in 43 years, all you need to invest is $3,000 a year. 43 years times $3,000. So you've invested about $130,000, but that $130,000 has grown to $1 million. All right, now, so this is 43.14167623. All right, so that's the number that would go here. And I'm just going to say about 43.1 years, because in this table, we're using most of these numbers. We want the future value to be $1 million. We want the interest rate to be 8. We want the compounding factor to be 1. And we're calculating T. And I put it in this row because our investment is 3,000, and that's what we invested up here. So I want you to redo this. If instead of investing 3,000 a year, you invest these other amounts. For example, if you only invest $600 a year, will you ever become a millionaire in your lifetime? Do the same calculation that we just did, and you can answer that question. Change the 3,000 to 6,000 and come back up and calculate. So this one is 63.7. So even at $600 a year, if you do it for 63, just add 63 years onto your current life age, and you can still become a millionaire in your lifetime if you continue that plan. But you can see if you invest less, it's going to take you a lot longer. And so I want you to fill in this table and then ask the question: does the payment have a significant impact on the number of years it takes to reach $1 million? All right, in the second table here, it's the same idea. And right here is where we put the 43.1, because it's the 8%. But what if the interest rate changes? So for example, if we had, let's say 13%, and we invested the 3,000. So it's assumed throughout in this table that you're going to invest 3,000. So the payment is always 3,000. The number of years is 31. So if you can earn 13% and you're making $3,000 payments every year, 1 per year, 3,000 the first year, 3,000 the second, If you do it for 31 years, you'll have $1 million. You can even retire when you're in your 50s or even late 40s for some of you. All right, so fill this one up and then say, answer the question below. Does the interest rate have a significant impact on the number of years it takes for you to achieve $1 million? Harley asks, are P/Y and C/Y are always the same? P/Y stands for, but I forgot what, okay. Payments per year is P/Y, and C/Y is the number of compounding periods per year. And usually we calculate interest at the end of each period. So if we're going to make, or coincides with the time we make the payment. And so when we make a payment, the interest is compounded. Make the next payment, that's when interest is compounded. And there are times if you do these problems where the two numbers are the same, they're not the same. It's just that for our problems, they will be the same because we're going to be working with ordinary annuity and we're working with models anyway. So all of these things that we're calculating are estimates. All right, this is a future value problem. Here's the formula. The only thing that's different in ours is I think our author uses an A here for future value and uses the little D for the they call it a deposit. But other than that, the entire, and I think we, instead of little m here, they use little n. Every book uses something differently, but this is a messy formula. It's messy just if you plug in numbers on the right-hand side. So what we're going to do to do these problems is to do the TVM solver. And you really are going to do the TVM solver hundreds of times in your homework and in class. So look for shortcuts as you're going through these problems. In this one, we're trying to figure out the time. Okay, so what is the time? T, 67 years, 63 years, 43 years, and so on. So this one we got from making a payment of -600. It says 600 here, but that's a payment, that's cash out. We start with 0. The interest rate is 8%. And we're going to find the T. So let's put a 0, oops. And we have 1 time per year. And then our goal, our investment goal is $1 million. We'll put that there. All right, so this is how we would calculate the 63.7. It says how long, and so the only variable in the TVM solver, and we understand that this one is m times t or n times t, little n times t, but we know that the n is 1. So it's 1 times t, and 1 times t is just t. So the n value that we find here is actually the number of years. Alpha, solve, and that's where we got the 63 number. And then over here, we change the payment, and that's it. Those 3 numbers stay the same in this problem. So 3,000, come back up and recalculate the number of years, 43.1. All right. Now, if we wanted to do this one, payment changes to 12,000. And when we go up and recalculate, I'll call it 26.5. All right, and then fill out the rest of that. I think we've got a lot of examples. I just wanted to go through maybe 1 or 2 more with you. For this one here, we have the payment is equal to 3,000. And in this one, the payment's always going to be 3,000, and the future value is going to be $1 million. And the M value is going to be 1. What we're changing here is the interest rate. Payment's always going to be 3,000. So we're always going to invest $3,000. We want to know how long it's going to take us to accumulate to $1 million at an interest rate of 8, because that's what the interest rate is here. And then when you come and calculate the number of years, you get the 43.1. Now to fill out the rest of the table, the only thing that you're changing is the rate. So this should be fast to fill out this entire table, because all you have to do, for example, for 13%, you would change I% to 13, and then go back up and recalculate the number of years, 31.0, 31.0. All right, just one more, so I make sure that I know that what you're doing here. Tell me what this is right here. How many years goes in this this spot. Go ahead and put it in the chat. You can round the number of years off to the nearest tenth like I'm doing here. All right, so here we have R is given as 9%. I suppose I could have given you the interest rates as percentages. But for this one, 0.09 is the R, that's 9%. So I change 9% to 9, and then come up here and recalculate. So if you round to the nearest tenth, it would be 39.8, close to 40. So you're just changing one number and then recalculating the n. Changing the rate, recalculating the n. Change the rate, recalculate the n. Ram, bam, bam, all the way down. You'll see that these numbers of years are decreasing, so that when you have a higher interest rate, the number of years that it takes you to reach $1 million, investing $3,000 each year, greatly reduces. So if you're a wise investor and you can get like 9% interest, then it's going to take you 40 years to become a millionaire if you invest $3,000 a year. And $3,000 a year is equivalent to $250 per month. Okay, so these ones down here, and you can talk about these in your groups. And it says, does the payment amount have a significant impact on the years to reach? And both of these are yes, but tell what that is. So as the payment increases, the number of years to reach $1 million in the future also decreases. So if you invest more, you'll become richer quicker. That's what that's saying. But you also have to be smart in what you choose to invest in. So you can't just save the money and put it into your mattress. Because if you put it into your mattress, that it's earning 0% interest. It's not earning anything. And so you want to invest it somehow. And so that's where the 401k comes in. These numbers here are the rates. These are the I percentages. So these are the different interest rates. And that's the I percent. So that's what you're changing. And so for this one, if it's 1%, now why does that make sense? Another thing is you do these more and more and more, you're going to see some connections. So you always want to ask the question, is that reasonable? And you know, when you're only making 1% interest, that's not a very high rate of return. That's like putting your money into a bank account where they don't pay you anything. And so if they're only going to pay you this tiny amount of interest, it's going to take you a long time to accumulate $1 million at investing $3,000 a year, right? We wanted to change only one thing as we go down the rows. Over here, we changed the payment, and then we looked at its impact on becoming a millionaire. And then this table is completely different, but what we're changing is the interest rate. That's the I percent. So you change the I percent, everything else stays the same, and you recalculate the M. If you increase your payment, you should become a millionaire quicker. If you get a higher interest rate on your rate of return on your investments, you should become a millionaire quicker. These two factors are important, and you got to work on both of them. These are the two that you can somewhat control. You can control how much you put in, and you can control where you invest your money. The problem with, you know, some of these higher interest rates is that when you invest your money and you're going to try to earn 20%, that means you have to take on more risk. And so your investments will go higher, might earn 30% in a year, but then they might also lose 30% in a year. So you have to be careful when you do risky investing, and that's why it's usually a good idea to leave it to somebody else. You know, pay somebody else, or don't pay them, but get someone else to invest your money. And most employers will have a human resources office, and you can set up appointments with these financial experts that come in, and they don't even charge you. Let's talk about your 401ks. We have a progressive tax structure in this country, and that means the more you make, the higher you're charged in interest. Well, let's go back to Clinton, Bill Clinton. And then there was George Bush, the second, and then there was Barack Obama, and now there's Trump. And after November, it might be Biden. And so when you look at the highest tax bracket on this, it's not on this amount, but it's close to this amount. On income, over 400,000. And I'm just saying 400,000 because Biden promised that nobody is going to have their taxes increased if they make, unless they make over 400,000. The idea is to tax at a higher rate those that can afford it, those who have the most money. And those of us that don't make $400,000 a year, we're not going to see our taxes increase. Now, if you look at the upper tax bracket, under Clinton, it was 39.6%. And what that means is that any amount of money that you make over 400,000, you're taxed at 39%. All right, Clinton was a Democrat. Then the Republican Bush came in, and Bush lowered it to 37%. Obama came in, and he didn't do anything because this tax cut right here had a sunset clause. And if the legislature didn't change the tax law, then the tax rates diverted back to what they were when Clinton was in power. And since the Congress couldn't decide upon lowering them or raising them, they just did nothing, and the interest in the tax rate on the wealthiest Americans went back up to 39.6. So just reflected back here. And now Trump came in, and then and lowered it back down to 37. And what Biden's suggesting, and he was a Republican, right? And what Biden, the Democrats, suggesting in his plan is to take it back up to 39.6. So the Democrats, raise the highest interest rate or the highest tax rate on those that make the most money. And then the Republicans come along and they lower that tax bracket. And then the Democrats come back in and they raise it, and you get the idea. So what Biden's proposing is that, well, let's just take it back to what it was, because we were given these folks making, a whole lot of money. We were giving them a big tax break. And here's what I mean by that. Let's say that someone makes $3,400,000. And let's say that this is their adjusted gross income right there. That's how much they make. Now, on most of that money, on the income over $400,000, which is most of this money, the $400,000 will be taxed at a lower interest rate. So $3.4 million, there are $3 million over the $400,000. And all dollars over the $400,000 line in the sand, I guess you call it, are going to be charged interest at the highest interest rate. So it's either going to be 37% under the Republicans, or it's going to be 39.6% under the Democrats. Now, let's just take a look at what the impact of this is. If you take 37% times 3 million, those that make 3.4 million have to give 1.1 million to the federal government. Might seem like a lot of taxes they're paying, but there has to be some cost for having access to the biggest economy in the world. If you take 39.6 times the 3 million, then you're at this amount. So here's how Democrats will reason. If someone's making $3.4 million a year, that's a lot of money. That puts these folks in the top 1%. And if you lower their taxes to 37% from 39.6, the difference between what they paid one year and what they paid the next year was $78,000. In the year 2018, when the new tax law began, when President Trump and the Republicans changed the upper tax bracket from 37% to 39.6%, somebody making 3.4 million just got sent to them a check for $78,000. Now, most Americans don't make $78,000, but that's what someone making $3.4 million just got in a tax refund, basically. What Joe Biden's saying is that, you know what? We don't want them to have that $78,000 for 2018, 2019, 2020, 2021, 22, 23, 24, because it went for 8 years. So the richest Americans are getting that $78,000 every year for 8 years. Joe Biden saying, you know what, I think if we just keep everybody else's taxes the same, but the richest most Americans, we're going to just take it down to 37. So they're going to pay this instead of this. They don't get the same tax cut as everyone else. And of course, they'll phase it out. But so this is the whole argument here. So Joe Biden is, going to raise taxes, but he's going to raise taxes on the richest Americans. And this is the math behind it. So I'm not asking you to calculate taxes here. But what I am asking you is to consider a real scenario of your own finances. And here's the scenario. Someone making $50,000, they could be offered from their employer a 401k. And a 401k allows the employee, you, to invest for your retirement. And right now in 2020, the most that you can put toward your 401k is $19,500. This is the law. Every year, because of inflation, they change it. Now, you might think that if you're only making $50,000, well, I mean, that might seem like a lot of money to you, but putting away for retirement $19,500 would seem like a lot. However, at some point in your future, you might have a significant other, a spouse, and living under the same household. And maybe both of you can put in this if you're working for companies. And if you don't work for a company that offers a 401k, then you can invest your money in what they call an IRA, individual retirement account. Some of you may have them already. But here's the advantage of investing in a 401k. When you invest in a 401k, the IRS treats that money that you put away as non-income. So if you make $50,000 and you don't invest anything, then you get taxed on all $50,000 of those dollars. If you make that same $50,000 and you invest $19,500 in a 401k, you subtract those two amounts and get $31,500. This is how much you get taxed on. So they don't tax that $19,500, even though it was income, because they want to incentivize you to invest for your retirement. This has dramatic consequences for investing. So we've talked about interest rates, and if you look at all of our interest rates that we've ever talked about, they are small numbers, like 2% interest or 5% interest or 8% interest. And what if I told you could earn 30% interest? Would you be interested? What if I said that you can earn 30% guaranteed interest without taking any risk whatsoever every single year? Would you be interested? Let's take a look at the math of a 401k. All right, so here it is. You make your AGI, that's your adjusted gross income, is $50,000. If you invested $19,500 in a 401k, then the IRS is only going to tax $31,500 of those dollars. All right, now I went through kind of the tax tables and I identified an effective rate that you would be charged for the federal government in the IRS when you pay your taxes. And so these may not be exactly right, but their relationship to one another is probably correct. So, and again, I'm going to do this one. So pay attention because you're going to be asked to do it in the groups here in a second. We're going to take 31,500 and that's your taxable income. And the federal government is going to want 6.7% of that. So we're going to multiply this by the decimal version of 6.7%. This is the amount that the IRS, the federal government, the US Treasury is going to want from you based on your income. So that's going to be an expense to you. Now, usually it's taken out, right, every paycheck. So at the end of the year, the amount of taxes that they've taken out of your check is probably equal to this. If they take out more, you get a refund. If they take out less, you have to send another check into the IRS. But I'm going to record this number right here, 2,110.50. The state of Michigan charges 4% tax, and it's 4% of, again, your taxable income. So the other one we have to multiply is 4% of that same 31,500, and that's 1,260. If you add those two amounts up, you get 3370 and 50 cents. So with state and federal taxes, $3,370 is what this person pays. This other person who makes the same income, $50,000, does not invest anything in a 401k. So they're at a disadvantage right now because when they retire, they might not have anything saved up. This person's going to have a lot saved up and will be able to travel, visit grandchildren, whatever they want to do when they retire with a little bit of financial security. These folks might only be living on Social Security when they get to retirement age. So other than just providing the basic food and lodging, they're not going to have a whole lot left over for anything else. Not too many people can live on Social Security alone. No, my mother's doing it, and many seniors are doing it. All right. Now, because this person over here has a higher taxable income, they have a higher taxable income rate, effective rate. So the federal taxes here are going to get a double penalty. One, because they make more money in terms of the eyes of the IRS, and because of that, they are charged a higher interest rate. So let's take 8% of this 50,000, 8.6% of the 50,000, and that is 4,300. So you can see that there's quite a lot more paid by this guy who makes 50,000 compared to this one who makes 50,000. This is double. All right. The 2% of the 50,000, well, that's 2,000. So together, this guy, if you add those two together, has to pay $6,300 in taxes. All right, I have these blanks here because I was intending for you to take the 4,300 and the 2,000, add those together, and then subtract the 2110.50 and 1260. So basically, this is the taxes, federal and state, of the smart investor, and these two are the federal and state of the person who didn't invest in the 401k. So we're going to take the 6,300 and subtract the 3370.50. So just arithmetic here. And here's the difference. Now, I've been talking about these people as if they're two different investors, but it's actually the same investor. One scenario, they invest in a 401k, and the other scenario, they don't. If they do not invest in a 401k, they have to pay this much more in taxes. This person here doesn't have to pay this much more in taxes. Since they saved this money in this year, you can think of it as, well, penny saved is a penny earned, right? Or a penny not paid in taxes is a penny earned. So if they're not having to pay this, then they've got this money left over. So what we're going to do is we're going to take that 29.29, that's how much savings there were. And if we divide it by the what was required to be invested, you can see that this interest rate is 0.15023, and as a percentage, 15.0. The goal of this problem is to identify this number, because by saving this 29.29 in that 1 year, because you save taxes, that money is sitting in your account. You can pay it or not pay it. And if you don't pay it, and what's required not to pay it is that you invest 19,500. So you do your rate of return divided by the total amount invested, you come up with a percent, and you can say, hey, by investing in a 401k, I've earned 15% on my $19,500 investment. And it's guaranteed. You're going to save it every year if you don't pay taxes. So there's an advantage. Here's an advantage of a 401k. Now, there's even a bigger advantage, because in some companies, I think I talked about this last time, your employer will match whatever you put in up to a maximum amount. I don't know of too many corporations that will give you 19,500 extra dollars. But what they do is they say, we'll match whatever you put in up to 3% of your income. So if the income, let's say, is $60,000, 3% of $60,000 is $1,800. If you have a company that matches the amount that you put into a 401k, If you put in this amount, they're going to put in this amount. And so $3,600 goes into your personal account instead of just what you put in, $1,800. And if you invest $1,800 and you get back instantly $1,800, then you've made 100% return on your money. You've doubled your money just because you invested. The results of investing in the data on the number of employees or the percentage of employees that invest in a 401k is astoundingly sad. It turns out that only about 20% of those who are eligible to invest in a 401k actually do it. They're giving away 100% return here, plus an additional 15% here. Okay, that's the one I wanted to show you. It's not future value problems, but it's more in a tax setting. And I want you to see the importance of investing in a 401k. Importance because your employer is going to match it, and important because you save in taxes. So even if you work for an employee that does not match it, you should still invest in a 401k. If you're going into the health field, a lot of times, they might give you 5% and you don't have to invest anything. In education, at Delta College, and most colleges and university, 10%, whatever I make, 10%, they put it into a 401k. And I don't even have to put anything in. So there's all different kinds of rules. And here are two problems just like the first one. And what I want you to come up with is the rate of return. And I think maybe you'll find that this rate of return is even higher for these other employees. Okay, that's the second problem. And the third one that I want you to work on in groups is this idea of saving and investing. Now, I know some of you are looking at me like, hey, I don't have any money. I don't even have a job. Some of you have jobs, some of you don't. Some of you are saving money in your job, others are not. Some of you might be earning unemployment, which is something that you should take advantage of. If you have been working and because of COVID or you're out of a job, you should take that money. You should take that money because this guy's taking that money. This guy's taking $78,000. Your unemployment check is not going to be $78,000. Okay, the next one is what I want you to realize here is that you have to start investing early. You have to start investing now when you're young, because it's unbelievable how fast this money will grow. And so in each one of these scenarios, you have Johnny on the spot and you have Johnny come lately. Johnny on the spot is the investor who starts early. As soon as he gets his first job, or she starts investing. Johnny come lately waits. I don't have any money. I'll do it when I'm making 60,000. I'm only making 40 now. All right, so I would like to work through problem A, and then I'd like you to do B, C, and D and E. Two friends save for retirement over a 40-year period in two different ways. Johnny on the spot starts investing at the beginning of the 40-year period, $4,000 per year at 8% interest for the first 20 years, and then doesn't invest anything in the last 20 years. Basically just $2,000 a year, every year for 20 years. And then at that point says, you know what, I'm going to stop investing because I think I have enough. So puts in $0 the rest of the 40-year period. So for the next 20 years, invest nothing. Now, during the last 20 years, his investments accumulated interest at 9%. Now, the other investor, Johnny come lately, didn't invest anything for 20 years, so waited. If he was 20 to begin with, then he waited for 20 years and started investing at age 20 or 40. So at age 40, he had $0 saved. But then he had enough money, so he invested $10,000 a year over the next 20 years at 9% interest. And the question is, who has the most money at the end? Who was the wiser investor? All right, I'm going to draw a little diagram to help us with this. The first one is going to be Johnny on the spot, and this is the early investor. And then I'll do another one down here for Johnny come lately. Waited. All right. I don't know what their ages are, but I'll just assume what they are. Age 20, age 40, age 60. I give you the age in other problems. I don't give you the age, I think, in this one. So from age 20 to age 40, that's 20 years. Same thing over here. Same thing for Johnny come lately. 20 years of not investing anything, followed by 20 years of active investing. And I'm drawing this this timeline here so that you can realize that in some cases we have to use two instances of the or two rounds of the TVM solver. Let's start with Johnny on the spot. Johnny on the spot invests over that first 20 years a investment, and that's the payment, of $4,000 every year. And there's no mention of the compounding factor because it says $4,000 per year. And consistently through this entire worksheet, it's the same. We're going to be talking about investments, one per year. So when you see per year, that translates into the n value, the little n value equaling 1. I sometimes write n, sometimes write m. Otherwise, it would say compounded quarterly, compounded monthly. Sometimes when it's just one time compounded annually, they don't say compounded annually. They say per year. All right, the interest rate here, all right, so Johnny's on the spot, invests $4,000 per year for the first 20 years, but then in the last 20 years invests nothing. The interest rate in the first 20 years is 8%, and the interest rate in the last 20 years is 9%. And we get all of this from the problem. I'll go back and look at the problem so you can match it up. Throughout this entire worksheet, I mentioned that the payments per year, compounding per year, the compounding factor is 1. So those two will just be 1 consistently throughout. And n is equal to little n times t, but little n is 1 and t is 20. So n is 20. Over here, same thing. All right. Now, the present value is the amount in the account. So when they start, at $0. Over here, $0. Now here's what we're going to do. We're going to use one formula where we're going to calculate the future value here to find out what he's going to have in the future 20 years later when he's 40 years old. That becomes the future value. Then what we're going to do is we're going to take all that money and invest it in this new account earning 9%, and we're going to figure out what the future value is here. So ultimately, we're interested in what is the future value at age 60 for both of these investors. And then we're going to compare these two. All right, let's work through it with the TVM solver. Okay, we're going to do the first 20 years for Johnny on the spot. In the first 20 years, we kind of wrote down many of these different variables. Let's put them all in. We know that n is equal to 20. The interest rate in the first 20 years is 8. We're going to start with $0 as the present value. And the payment we're going to make is the $4,000. We'll enter it in as negative 4,000. Payments per year, compounding per year will be 1. And what we want to calculate is making that payment every year for 20 years, how much they have in the future. And by the future, we mean age 40. So we're going to calculate this using the AlphaSolve. And you can see that they're like $183,000. So the present value of this investment is 183,047, and we'll say 86. This is the present value when the second 20 years begins, but it's actually the future value of this problem, this first half of the problem. So let me write this down. This 183,047.86 is the future value here, but then we're going to turn around and we're going to invest it here. So the present value here becomes what the future value was at the end of the first 20 years. So what we're going to do is we're going to take this amount, put it in as a negative, because again, we're investing it. And let's go to the second part of the problem. Okay, we've already settled that at the end of the 20 years, we're going to have this amount of money at age 40. Very nice. If you have saved $183,000 when you're 40, you can consider that a success. All right, what's going to change? In the next 20 years, it's no longer an annuity because the payments have stopped. This is a lump sum problem. And so we're going to n Well, n is still the same. The interest rate goes up to 9. And the present value is now, I'm going to type in this negative 183,047.86, and then no payment. Payment equals 0. So here are the inputs. Payments per year equals 1 still. And what we eventually want to do is to calculate the future value. So the first half of this problem was an annuity because we were making regular payments. And the second half of this problem, we just take the money that we earned in the first 20 years, roll it over into a new account, and just watch it earn 9% interest every year. And at the end, that $183,000 turns into this amount. And that amount is over $1 million. So this is how you become a millionaire in your lifetime. And how much did you have to invest in order to earn $1 million by the time you retire? Well, you didn't make any payments here. So no money came out of your pocket here. You just took the money that you earned in the first 20 years and reinvested it. And how much did you invest here? $4,000. How many times did you make that investment? 20 years. Every year for 20 years, you put away $4,000. And $4,000 per year times 20 years, $80,000. So you invested $80,000, and at the end of 40 years, it has accumulated to over $1 million. This is not magic. This is mathematics. It's called compound interest. And in order to make this amount over here, you have to start early. 80,000 becomes $1 million. Now, I will have to say that, these are nice interest rates. And if you can get that interest rates, you can be very happy with yourself. Okay, let's take a look at our friend Johnny Come Lately. Now, Johnny Come Lately, if you recall, he didn't put anything away for those first 20 years. So while Johnny on the Spot had over $183,000 saved up after the first 20 years, that 80,000 changed into 183,000. Our friend Johnny Come Lately didn't invest anything in the first 20 years. So at age 40, his 401k has $0 in it. He knows he has to catch up. So he's going to invest $10,000 for 20 years, and he's going to invest $200,000. $10,000 is the payment for 20 years. Well, if Johnny on the Spot invested 80,000 and ended up with over $1 million, then certainly Johnny Come Lately, if he's going to invest more of his own money, 200,000, 2.5 times more, $120,000 more over that 40-year period, he should have more, right? All right, so N is equal to 20, because we're only focused here, because there's zero money here. The present value is equal to 0. The interest rate is 9, and we need to calculate the future value. It's 9 because apparently in these last 20 years, the going interest rate was 9. So Johnny on the Spot got that same 9, and he only got 8 back here. Had he gotten 9 back here, then this amount would even be higher. All right, let's figure out in those 20 years how much Johnny Come Lately will have. Start with 0, invest $10,000, 20, 9, 0, negative 10,000, and we want to calculate how much he'll have in the future when he turns 60 and gets ready to retire. So alpha solve, and we'll write down this number, 511,601.20. Right, so that $200,000 did grow to $500,000. This is a very nice nest egg here. So he's to be commended on his investment. However, look at the difference. Johnny on the Spot invested only $80,000 during that 40-year period and ended up with over $1 million. Johnny Come Lately invested $120,000 more than Johnny on the Spot, but only ended up with half the amount after the 40 years. So this is the power of starting early. All right, there's a table for each of these. So maybe I'll copy down this table and show you how you would fill it out. All right, so we have Johnny on the Spot and Johnny Come Lately. Age at first investment. Johnny was 20, Johnny on the Spot. Johnny come lately, remember he waited 20 years. So his age when he started investing was 40. Number of years investing. Well, Johnny on the spot actually had 40, but remember it was 20 making a payment and 20 with no payment. But still, in that last 20 years, the money that was in his account was still earning interest. So you got to say that he was still, being an investor, an active investor at that point. Johnny come lately, just 20 years, from age 40 to age 60. All right, the next one is the annual investment. Now, we have to say that it's the annual investment when they're actively, making an investment each year. So it was $4,000 for Johnny on the spot and $10,000 for Johnny come lately. The APR, the annual percentage rate. All right, so it was 8% for the first 20 and then 9% for the last 20. And for Johnny Johnny come lately, it was 9% during that last 20-year period when he was an active investor. Total amount invested. So this table is really just kind of a table to keep all of your numbers organized. All right, so this was $4,000 times 20 years, 80,000. We did that calculation before, and this is $10,000 times 20 years, and that's 200,000. So we've done all these numbers. It's just a matter of taking the stuff from up here and putting it in, organizing it in a table. And that's what we're doing now. And the last thing is that we want to know what the future value is. And this is at age 60, because they started at age 20, and then they're looking at the future value. And these would be the two amounts that we calculated. The first one is $1,025,875 and say 40 cents. And the other one was just over $500,000. How much did Johnny on the spot invest? Right. The total amount invested was $80,000. How much did Johnny come lately invest? 10,000 for 20 years. And then the next question says, how much did they accumulate? Well, Johnny on the spot, that was the over $1 million number. And Johnny come lately, that was the just over $500,000 number. So both are wise investors because at age 60, they have at least $1 million or $500,000 in their account. All right, so who is the wiser investor? Clearly Johnny on the spot, since he invested $120,000 less, yet earned $500,000 more. And all because he started early. So I'd encourage you to, for each one of these problems, to, draw a diagram like we have. This is the second one. This one I give you the table. Compare the future values of the two Johnnies in the scenario below. Johnny on the spot starts investing at age 25. Invest $3,000 for 30 years. Payments per year, compounding per year equals 1. There's no mention that we're going to have compounding other than once per year. For 30 years, okay, that would make him age 55 here. So 30 years. And then from 55 to 65, that's 10 years, he invests nothing. So this is very similar to the problem that we just did. Kind of a two-step problem. One, the first part is an annuity, and the second part is just a lump sum investment. Johnny come lately begins investing at age 30. All right, so we say age 25, age 30. So here's the start for Johnny on the spot, and here's the start of investing for Johnny come lately. Johnny come lately begins investing at age 30 and invests $3,000 for 30 years. Same as Johnny on the spot. All right, so age 30, then that would put him about right here at age 60, from 30 to 60. And then from age 65 to 60 to 65, in here, he invests no additional funds. So the payment here, n is equal to 5 for 5 more years, and the payment in this last chunk is, oops, you don't even see that. There it is, sorry. Here's Johnny come lately. He starts investing at age 30. So there's no money made in these first 5 years. And then for the next 30 years, from age 30 to age 60, 30 years, Johnny come lately is investing $3,000 a year. Notice that both of these guys, both of them invested $3,000 for 30 years. $3,000 for 30 years. So both of them invested $90,000. The only difference here, and they both retire at age 65 and they want to figure out what their future values are at that point. Future value equals what? The difference between these two investors, they invested the same amount of money for the same number of years. They're the same age. They both retire at age 65, but one of them started 5 years before the other. How are these two numbers going to compare? If you just wait 5 years. That's problem number 2. So I'll let you guys work on that in your groups. It's 3:28, so let's take 10 minutes and we come back. I might get you started on the third problem and then we'll put you into the groups. So this one is part B. All right, so again, the problems are similar. They're going to invest over a big chunk of their work life. Part of it they might be actively investing, part of it they might be just letting the money grow. So let's compare the two Johnnies in the scenario below. So Johnny on the spot invests for at age 20. This one here is C. At age 20 and invests $3,000. So there's a regular payment being made each year for 45 years. Okay. And this is a pretty consistent investor. And every year up until age 65, I'm going to invest the $3,000. So the total invested over that period of time would be 45 years, each year investing $3,000. So that is a total of $135,000. All right, so there in this particular one, there was not a period where he stopped investing and just let the money grow with the interest rate. By the way, I think in most of these problems, like part B, I'm just assuming that they're going to earn 7% consistently throughout the period. So that's the same thing we're assuming here, 7% per year. All right, Johnny come lately, let's read it and then I'll draw the diagram. He begins investing at age 40 and invests $10,000 for 25 years. So at age 40, if you tack on 25 years from that, you'll be 65. But doesn't invest anything before that. All right, so let's draw Johnny come lately's diagram. At age 20, nothing. Age 40, okay, no investing here. But from age 40 to age 65, that's 25 years at an interest rate of 7%, starting with nothing here, whereas Johnny on the spot started with nothing here. And the payment here is $10,000 for 25 years. So the total investment for Johnny come lately, there were 25 years of investing, $10,000. So that's a total of $250,000. So here's another scenario where Johnny come lately invests $250,000, whereas Johnny on the spot only invests $135,000. But Johnny started earlier. So I wonder if Johnny come lately will catch him. This next one is going to be similar. And the first one, if you think about the Johnny on the spot, then the whole problem was premised on there's a period while you're working and you're accumulating wealth. And you can accumulate wealth by saving and investing, putting away a little bit of money each year. And I think you saw that in one case, $80,000 turned into over $1 million. But now comes the benefits of all your work. And when you save and you have a $500,000 or $1 million, by the time you're retired, you can then retire, and then you get to pay yourself from all that money that you've gained. It's not like we go ahead and do all this work and invest and save this big chunk of money, to be able to pass it down to our kids or give it away to charity, although hopefully you'll do some of those things. But we really just need to live comfortable in our own life. And if there's a little bit more left after we die, then yeah, the kids can have that. But you want to make sure that you're not living in poverty where you have to work when you're a senior. So the next part, this part that we're going to work on right now, is that, okay, now that you've saved this money, now let's see how it's going to turn out for you and how much you can actually pay yourself in retirement once you've accumulated that nest egg. So let's take a look. This is Finance 2, and this is also an e-learning, Project 6. This is the 6th one of, I guess, 10? Are there 10? So they're not that many. There's fewer left in the second part of the semester. All right, here's what we're going to do. We're going to start what we call is a retirement annuity. And at the time they retire, so just think about all those problems where you ended up with 730,000 or $1 million or something else. These folks only save 200,000 in an account, and that pays 8.4% compounded monthly. So it's sitting in that account, and they're making a nice interest rate. If they keep it in that account, they will continue to earn interest, but they need money to live on. So they want to withdraw equal monthly payments for 10 years. They figure that at age 65, in 10 years, they'll be 75, and they won't need the money anymore. Maybe they think they're going to die at that point, or maybe they have a life insurance policy that they can collect on when they turn 75. There's lots of different reasons. So at the time they retire, if we're going to do an annuity, we're now looking at the present value annuity problems. So that's what this project is all about, present value. So this is, you have a bunch of money, a present value at the beginning, and then you want to dole out that money in small chunks each month for the rest of your life. Basically, that's what it is. So the amount that they've saved from the time they start paying themselves, this is the present value of their account, and it's sitting in there. They tell you also in the first part of this problem that while it's sitting there, it's earning 8.4%. So that's 5%. It's compounded monthly, so the little n is 12, but that means that payments per year and compounding per year are also equal to 12. So a lot of this is similar to what we've done. It's just a matter of matching it. It's a different context, so that's why you gotta pay attention to, what changes. Okay, so this is kind of the stem of the problem. We don't have all of the values of the variables to enter into the TVM solver, but we have many of them. Let's read on to problem A to see what else we can figure out. The couple decides to withdraw monthly payments for 10 years. So T is equal to 10. And if you put the N and the T together, N, because of monthly payments and monthly compounding, would be 12, and the number of years would be 10. So they're going to be 120 equal monthly payments of this money over a 10-year period, at the end of which time in the account will have a zero balance. So the future value of the account is 0. How much should the couple withdraw each month? Well, that is the regular period payment, but they're paying it to themselves. So put everything into the TVM solver that we know in this problem, and let's calculate the payment. All right, the T is 10, along with N is 12, multiply them together, so N is equal to 120 monthly payments over 10 years. The interest rate was given to us in the stem up there at the top to be 8.4. The present value is how much is in the account. That's going to serve as the amount that we can withdraw from, and that is 200,000. In present value annuity problems, the present value is positive. That's not money coming out of our pocket. It's just kind of sitting there. The payment is what we're going to try to figure out, and at the end, we'll have 0 in the account, and we want to make 12 payments per year, and the interest will be compounded at the same time. And the one we want to calculate is the payment. All right, so how much can they pay themselves each month if they've saved $200,000 over their working career? We do an alpha solve here. All right, and that's a monthly payment. So we're going to convert it to an appropriate format, round to the nearest penny. So every month for the next 10 years, they can pay themselves $2,469. Every month. Every month, first of the month, they get a check. They've got it set up through auto deposit. Just goes from their investment account right into their bank account. Now keep in mind that seniors also get Social Security. So seniors that have worked all their life, they get probably about $2,000 every month from Social Security. So add the Social Security $2,000 to the money that they're paying themselves from their own annuity, and they're bringing in, you know, $4,000. That's each individual. Well, this is a couple, and then each individual would get Social Security if they've worked. All right, let's take a look at the next problem. It's slightly different, but you can see that Part A was just a one-step problem with the TVM solver. All right, so if instead the couple decides to withdraw $3,000 a month, that's a little bit more than what we calculated they could withdraw each month over a 10-year period. So now what they're saying is that, well, what if the payment is $3,000? How many withdrawals can the couple make? So what we're looking for is the number of months, and that's N. How much time, how many withdrawals? The number of withdrawals correspond to the number of months that they still have money left until the balance of the account is zero. So once again, the future value is zero. But everything else in this problem will go up to this information up here. So the N is what we're looking for. The I percent is still the 8.4 as stated in the original problem. The present value is what they've saved over their working career, still the 200,000. The payment, negative 3,000. The future value is zero, and the payments per year, compounding per year, is equal to 12. So we're still going to have 12 payments per year, but instead of the 2,469, they want to pay themselves a little bit more, 3,000. 90.1151758. All right. They're not going to have another full payment. They won't have a 91st payment because after they have the 90th payment, they won't have much left. So what we would say here is about 90 months of payments. And if you divide 90 by 12, because there's 12 months in a year, that's about 7.5 years. So they can pay themselves $2,469 a month for 10 years. But if they want more than that, if they want the $3,000, it's going to suck money out of that 200,000 a little faster. So it's not going to last as long. And you can see it lasts 2.5 years less because they took out that extra amount. Okay, so here's kind of the example problem, number 54 here. And then what I'd like you to do is to, basically do two problems just like it. What I've changed here is I've changed the amount of money that they've saved and a different interest rate. But most of these are monthly because generally when you retire, when you get paid each month periodically. All right, this probably will be, well, they get increasingly difficult as you kind of go through the problems. And all right, so the best way to do this one is probably with one of those charts that kind of a timeline that we have. So let's read it first, and then we'll try to set up a timeline so we can figure out what the two parts are. Person establishes a sinking fund. A sinking fund is a future value problem for retirement by contributing $7,500 per year at the end of each year for 20 years. For the last 20 years, equal yearly payments are withdrawn, at the end of which time the account will have a zero balance. If the money is earning worth 9% compounded annually, what yearly payments will the person receive for the last 20 years. All right. So this represents a 40-year period. We've got 20 years, and then we have the last 20 years. So in the first 20 years, this is where the sinking fund occurs. And then after that 20 years, they retire. And for the 20 years that remain after that, they're going to do what we did in that previous problem, which is they're going to start an annuity and they're going to pay themselves until it's zero. So the sinking fund is a future value problem, and the annuity is a present value problem. And since one's a future value and one's a present value, you can't use the TVM solver once. You got to use it twice to answer both pieces of this. All right, so I guess, what I tell students is just think about the first half of the problem and write down all the inputs to the TVM solver. And it might appear that you have fewer values than you need to answer the problem, and do the same thing with the present value problem. All right, so we're going to focus in on the sinking fund up here first. They contribute $7,500, and that is the annual payment. And interest throughout this whole problem is compounded one time for 20 years at an interest rate of 9. In this problem, they start with 0, present value 0 here, and then after the first month they have 7,500. After the second month they have 15,000, and not month, year, because these are yearly amounts. If they make 20 payments of 7,500, they will have contributed $150,000. But because some of those $7,500 payments were made early, they were accumulating interest. So the first thing we have to do is to find out how much is in the account after 20 years, and then that would serve as the present value in the second part of the problem. In the second part of this problem is just like the problems that we just did in the first part of this project 6. In the second part of the problem, money's still sitting in that same account earning 9%, 20 years in retirement. The present value will be what we start with in the second half of this problem. But we first have to figure out in the sinking fund, what is the future value after the first 20 years? Then at the end of the next 20 years, there's $0 left in the account. You spend it all. And throughout this problem, we have 20 years, 20 times 1 payment per year. So in the second part of this problem, it looks like there's 2 things that you don't know, but that's okay, because the first one you're going to calculate here and then move over to the second part of the problem. And you do have everything you need here. Okay, so first thing I'm going to do is to calculate the future value if we invest 7,500, a total of 150,000 over 20 years. What does that grow to? So N is 20, and then the interest rate is 9, and we start with 0, but we make $7,500 payments each year, 383,700, and I'll round it. Well, I won't round it yet. Now this is what this is the future value after 20 years. Then we retire, and then we pay ourselves from this chunk of money. Just like in our previous problem, the amount that we've saved is the present value. So this couple saved $200,000, and they used that to make payments to themselves for 10 years. So what was the future value in the first part of the problem becomes the present value in the second part of the problem. And this one I'll round to 90 cents to get as close as we can. Now we're going to enter in these numbers and calculate the amount we can pay ourselves once per year for 20 years. So if these folks are, say, 65 years old, or this is a person, so if their age is 65, then they can pay themselves this amount of money for 20 years until they're 85. And I know it's a strange thing, but right now I'm doing this. I have to ask myself, if I retire, at age 65, how many years am I going to live? Nobody knows. But, you can look at the date, like I can look at the age of my father when he died and his father and kind of get a sense. My wife can look at her mother and her mother's mother to try to get a sense of how many years you're going to live after you retire. And then you base the amount you pay based on how many years you think you're going to live. Negative 4203,383,700.90 And I think everything's the same. We want to end up with $0, $42,033.08. Now that's per year. So if we did want to know what the monthly payment would be, we could divide this yearly payment by 12. And this is per year, or we could say 3502.76 per month. So that's a nice chunk. Now let me just go through the math here, and we know that this guy invested $150,000 of his own money. But what did he get paid back over those last 20 years? What he got paid back over those last 20 years would be $42,000, a little bit more, times 20. That's 840,661.60. I mean, I don't know if you know if you can see how significant this is. With this $150,000, the $7,500 that this guy invested each year, he put out $150,000 of his money, but in return, he received $840,000. 150 turned into 840. This is how annuities work.
So, Mr. Ham, you didn't plug the 150 in anything, did you?
No.
Okay.
But it's something that if you wanted to know what interest he earned, you would need to know that number. You'd need to know how much he invested, what he ended up with. So for example, you could take the 383,700.90 and subtract the 150,000 to learn that $233,000 of that total amount that you have after 20 years is interest. Not interest. You might as well pay yourself that interest instead of paying it in loans to the bank. All right, so these problems, and I'm asking you to do 2 more, 3 and 4, just like it. Draw a picture like this. You're going to do a sinking fund or a future value problem in the first half, and you're going to do a present value payout, just like the first problem that we did on this worksheet, in the second half. And they might ask for yearly payments, or they might ask for monthly payments. All right, and the last problem, if you've looked at the document I put in e-learning, it's a 3-step problem. And in this one, we are going to refinance our home mortgage because the interest rates have come down. And one of the things that you're going to want to do in managing your finances is to manage your debt. Pay the least amount of interest that you can. You're not going to get away with not paying interest if you buy a house, because when you buy a house for $200,000, most people don't have that amount of money sitting around kind of under their mattress. So you have to borrow it from a bank, and that means you're going to pay a lot of interest. But you don't want to pay more interest than you need to. So the refinancing problem is this. This person purchased a $200,000 home 20 years ago by paying a 20% down payment and then signing a 30-year mortgage. And the rate back then was 13.2. Right now, if you were to buy a house and you went to get a loan, the interest rate's more like 3.5. So it was huge back then. And this is the reason why you would want to refinance your loan. Anyone can do it. You have to pay a fee. You might even have to pay a $2,500 fee just to refinance. But the amount of money that you will save over the life of the loan far exceeds the $2,500 that you would pay up front. That's what I'd like you to see in this problem. So it's a 3-step problem. And if you break it down into pieces, it's not too bad. The 3 pieces are, number 1, figure out the original monthly payment. And you've done this many, many, many times already. The second step is to figure out the present value of the loan after so many years. And in this case, it's after 20 years. And this number will vary from problem to problem. So you'll see that in your other problems, they're going to refinance after, say, 5 years or 10 years. And the third part of the problem is to determine your monthly payment on the new loan. Okay, so a person purchased a $200,000 home, but then we have to subtract 20% down. So we have to subtract 20% of the 20,000. Banks generally will not loan you a mortgage like this unless you put 20% down. If you happen to be eligible for less than that, and the government has programs every now and then that'll create these new programs to allow more people to get into homes, then you might only have to put down 10% or 5%, but that usually comes with this extra fee, insurance fee, so in case you default on your loan. All right, 20%, remember that's 0.20 times the 200,000, and that's 40,000. So the loan amount that you have to take out is not the 200,000 because you've actually paid down the 200,000 by 40,000. So the money that you have to borrow is only the 160. And that there is the present value of the loan. There are going to be 360 payments in the original loan because it was a 30-year mortgage with monthly payments. The interest rate was huge, 13.2%. The payment is what we want here. So the original payment is what we're calculating here. So that's the one we're going to calculate. And in all of these problems, the payments per year, compounding per year, would be 12, because when you buy a house, you're going to have monthly payments. And at the end of the loan, you're going to owe nothing. Monthly payment should get a negative. What do you think? You want an expensive house? You have a big payment. Okay, in the second part of this problem, we're going to try to figure out, we want to refinance after 20 years. So what happened is the interest rates came down quite dramatically. And you can see in this problem that the interest rate came down to 8.2%. It used to be 13, now it's down to 8.2.
Okay.
All right. The first thing we have to do is to calculate the present value of the loan after 20 years. We're not going to change the interest rate here until the last step. That's
Okay.
when we change the interest rate. The payment that we have here is talking about the payment of the original loan. So I'm just going to bring the payment that we calculated in part one, just bring it on over. I will round it. You don't have to. So it looks like that. Now, the
Okay.
tricky part about this one is calculating n. Now, at the beginning of our process, the n was 360. So the way that you interpret that is the number of payments that remain on the loan. Number of payments remaining. So we started with 360. After 20 years, 20 times 12 is 240. There were 240 payments made. So there are only 120 payments remaining on this loan. So to get the present value, we leave most of the loan information in the problem. That is the same compounding factor, the interest rate's the same, the payment's the same. But what we're going to change is the n, because there's only 120 payments. What is the present value when 120 payments remain? This is what will give us the present value after 20 years.
Okay, so we're not using what's in N right now, or we are?
Yeah. We're going to get rid of it and we're going to change it to 120. We're going to change that one number, and then we're going to go down and calculate the present value. You see, you no longer owe $160,000 on the loan because you've been making payments over the last 20 years. What do you owe? Well, we'll calculate the present value.
Okay.
And the present value is 119,272. So even after making 20 years worth of payments on this 30-year loan, we still owe $119,272.60, let's say. Oh, well, I didn't round this number. I just left it in there and went with that. So if you're off by a couple of dollars or a couple of pennies, you don't have to worry about it. Now we're going to go to the last step. And the last step is where we calculate the new monthly payment with the new interest rate. And the new interest rate in this problem is the 8.2. The present value, we're going to bring over from the previous step. We're going to bring over the rest of the information as well. What's going to change is the payment, because we're going from a 13.2% interest rate down to an 8.2% interest rate. But most of the other numbers, they just stay the same. Okay, so we're going to bring over this present value number, because that's how much we owe. Okay, and it says that they're going to refinance the unpaid balance. So here's the unpaid balance. They're going to refinance with a new 10-year mortgage. And that's why this is 120, because you've got a new 10-year mortgage of monthly payments, 10 times 12. And then redo the payment. Is that what you got? A lot of math students will forget a lot of the math they've learned. What you need to take away from this class is that there are problems like this out there. And take away from this class, not the weeds, all the details here, but just that, you know what? You should start investing as early as you can, and then you'll be able to live comfortably in retirement. How much interest will refinancing save? I mean, the whole purpose of doing the refinancing is to, save yourself some money. So let's find out. And I'm just going to do this. This is not a TVM solver problem. This is the interest without refinancing. So what we're going to do is we're going to calculate the interest that you pay if you don't refinance, and then we're going to calculate the interest that you pay with refinancing, and we're going to subtract the two to find out how much you save. All right. Now, if we didn't refinance, then we would make our original payment $1,794.97. We would make that payment 360 times. This would be our total payments. If we subtract out the original amount of the loan, which was $160,000, everything else would be interest. So 1794.97 times 360 minus 360,000. And I'm sorry to report that this is close to $500,000 in interest. Now, if we did do the refinancing, we only made this payment 240 times. And the remaining 120 payments were a little bit lower. But then we subtract out the original loan, and everything else is interest. So this is a little bit longer of a calculation. $445,961.60 of interest. All right, so to figure out how much we've saved, we're going to take the bigger interest amount and subtract off the smaller interest amount, and everything we have left is our savings. The one number in there already, so I'm just going to subtract this number, and you can see it's about $40,000 in savings. If you take out a loan for $160,000, what's worse about this is just the huge interest rate. And that's why there's such a huge interest here. You can see that refinancing was a smart idea, because in the end, you've saved yourself $40,000. And all you did was fill out some paperwork. You just have a smaller monthly payment because the interest rate came down.